Hello, everyone, and welcome to part 3 of our webinar series, Irrigation of Controlled Environment Crops for Increased Quality and Yield. Today's presentation will be about 30 minutes, followed by about 10 minutes of Q&A with our presenter, Dr. Gaylon Campbell, whom I'll introduce in just a moment. But before we start, we've got a couple of housekeeping items. First, we want this webinar to be interactive, so we encourage you to submit any and all questions in the questions pane, and we'll be keeping track of these for the Q&A session toward the end. Second, if you want us to go back or repeat something you missed, don't worry, we'll be sending around a recording of the webinar via email within the next 3 to 5 business days. All right, with all of that out of the way, let's get started. Today, we'll hear from Dr. Gaylon Campbell, who will discuss how to calculate water requirements for crop steering. Dr. Campbell has been a research scientist and engineer at Meter for over 20 years, following nearly 30 years on faculty at Washington State University. His first experience with environmental measurement came in the lab of Sterling Taylor at Utah State University, making water potential measurements to understand plant water status. Dr. Campbell is one of the world's foremost authorities on physical measurements in the soil-plant atmosphere continuum, and his book, written with Dr. John Norman on environmental biophysics, provides a critical foundation for anyone interested in understanding the physics of the natural world. He's written 3 books, over 100 refereed journal articles and book chapters, and has several patents. So without further ado, I'll hand it over to Gaylon to get us started.
Well, thank you, Brad, and thanks for being with us today to talk about the water requirements of controlled environment crops. As Brad said, this is the 3rd lecture in a series on this topic. And before we start talking about the calculations, I'd like to review some of the things that some of the main points from the first 2 lectures. The first lecture was on the hydraulic properties of the substrates that we use to grow horticultural crops. And we talked about the jobs that we hire a substrate to do. Its purpose is to supply water and nutrients to the plant and oxygen to the plant roots. We talked about the 2 quantities that describe the state of water in the substrate, the water content and the water potential. And we investigated the relationship between those 2 variables for typical horticultural substrates. We showed that even the lowest water contents typically used in these coarse textured media, no significant matrix water stress could occur. And so stressing the plant by reducing the water content is not something that's in the cards. Finally, we showed how to accurately monitor water content in these media and how to use the water content data to maintain the exact right growing conditions for the plant. The second lecture, we focused on the measurement of nutrient concentrations in substrates. We showed that we could accurately predict the concentration of nutrients by monitoring the electrical conductivity of the water in the substrate pores. But to determine that concentration, we needed accurate measurements of the bulk electric conductivity and the water content of the substrate. The root environment is dynamic, and so continuous monitoring is needed to correctly manage the root environment. Besides telling us the nutrient concentration, electrical conductivity also tells us the osmotic potential of the root zone, which is a measure of the water stress that the plant might be experiencing. And this is what we manipulate to give vegetative or generative cues to the plant for crop steering. Again, careful and timely monitoring is important, and Meter's Arroyo system makes that possible. Much can be accomplished by just following water content and pore water electric conductivity values over time and keeping those within set limits. But if we want to schedule irrigation, we need to be more quantitative. We need to know how much water is being applied and what happens to it. A good context for the discussion of those quantities is the water budget or the water balance that I've shown in this slide. The water balance states that the change in water in the plant and the substrate, we've called it delta storage here, has to equal the irrigation amount, I, minus the evaporation amount, E, and the drainage amount, D. And we'll take a look at each of those terms in turn. Now, if we'll start by the irrigation amount. If we're using drip irrigation, then the number of milliliters of water we apply per plant per day is the product of the number of drippers we have per plant, the flow rate per dripper, and the number of minutes per day the irrigation is on. Now, this might seem pretty simple, but it's extremely important to get it right. This is the basis for calculating all the other components in the water balance. So let's assume that we have 2 emitters per plant, that each of them is rated at 1,200 milliliters per hour or 1.2 liters per hour. We'll assume that our daily irrigation consists of 6 shots, each of which lasts 5 minutes. So we irrigate for 30 minutes per day. We also assume a substrate volume of 6 liters, and I'll show what that's for in a minute. Our emitter rate is per hour, and so we need to convert that to per minute. So we divide the 1,200 by 60 to get 20 milliliters per minute. And then we use our formula, 2 emitters times 20 milliliters per minute times 30 minutes per day gives 1,200 milliliters per day or 1.2 liters per day. And that's our irrigation rate, the I term in our equation. Now, another calculation is needed to give the volume per shot. Each shot is 1/6 of that, or 200 milliliters. And to calculate a shot volume, we use the same equation as for the total, except we put in the time per shot. I've shown it as a small t rather than a large T here. Now, to avoid channeling, we want the shot size to be small compared to the substrate volume. If we divide the 200 milliliters by 6,000 milliliters, the substrate volume, we see that our shot size is about 3.3%, and that's appropriate for vegetative steering. We go higher than that when we're doing generative steering, but would like to keep it below 10%. Now, if your irrigation is not uniform, your crop production will not be uniform, and you'll waste water and nutrients and production potential. So you need to assure that the emitters are accurate and that the water application is uniform. And to do that, you need to check the output from a representative sample of drippers. To do that, put the drip stakes in a cup, turn the irrigation on for a set time, say 5 minutes, measure the water in the cup, and calculate the rate. The amount that you get from the different measurements you make should agree within a few percent of each other and should agree with the amount that you assume you're applying. Let's now go to the evaporation term, the E term in the equation. That includes both the water that evaporates from surfaces and the water that's transpired by the plants. In controlled environments, the exposed evaporating surface is often small compared to the evaporating surface of the plant. So we'll mainly focus on the water that's lost by the plant. The factors that affect evaporative loss are the leaf area, the stomatal conductance, the radiation, wind, temperature, and vapor deficit. Now, you might be surprised that the lights affect the evaporative loss. But what you need to remember is that it requires 600 calories of heat to evaporate 1 gram of water, and the lights, along with the air, supply that heat to evaporate the water. Here's the equation that we use to compute transpiration. If we just look at the main parts of it, it's the product of a fractional interception of light by the canopy. So the fraction of light the canopy of the incident light the canopy intercepts, a vapor conductance for the leaves and the boundary layer, the difference between the saturation vapor pressure at leaf temperature and the vapor pressure of the air. We divide that by the plant density to convert from milliliters per square meter of bench area to milliliters per plant. So now if we knew the canopy temperature, we could easily compute the transpiration rate, but we don't normally know the canopy temperature. It won't be equal to the air temperature because of the radiant energy that the canopy is absorbing. So we need to compute a leaf temperature. And that takes an even bigger equation. Now, I won't talk about all of the variables in this equation, but the most important ones are the air temperature, the absorbed radiation, the vapor deficit of the air. If we start with the air temperature, then we add a component that's from the absorbed radiation, and we subtract a component due to evaporative cooling. The heat and vapor conductances are a part of the calculation, but they're included in the variable that we show as gamma star in this equation. We don't have time today to go through the details of the calculation, but the things I want you to take away are these: that the theory is sound for doing this calculation. It's been successfully used many times in practice. The equations certainly are big, and there are a lot of them, but they're easy to implement on a computer. You don't do these calculations by hand. And all of the inputs that are needed to do these calculations are quite easily measured. We need air temperature, the fractional interception, the stomatal conductance, radiation wind, and vapor deficit. And here are some of the ways that we can get those data. In the upper left, show the canopy and the Arroyo nose. The nose has a solar panel in it, and that's used for charging its internal batteries, but it also is set up so that it's useful as a light sensor, since there are nose modules below and above the canopy. We have measurements of light below and above the canopy, and the ratio of those gives us the fractional interception. The picture on the right shows the apogee pyranometer, or the apogee quantum sensor hooked up to an Arroyo nose, and that's mounted above the canopy and gives us the light interception information that we need for doing the calculations. The lower left picture shows the meter SC10 leaf barometer clip clamped onto a leaf to measure stomatal conductance. That's a manual measurement, but if we make those measurements on leaves during the light period and during the dark period, those measurements will be can be applied over longer periods of time, and we can use those to do the calculation. In the bottom center is the Arroyo climate station that can give us the air temperature and the vapor deficit and accurate measurement of that. And finally, on the lower right is a sonic anemometer, the Atmos 22 per meter, that could be used for monitoring wind, although wind probably stays fairly constant in a typical controlled environment situation, and that could be measured manually and input that way. Now, moving on, we want to talk about measuring drainage and change in storage. And to do that, I'd like to show results from an experiment that we did last summer in a controlled environment chamber that you see here in the picture. You see plants growing in 3 different substrates: cocoa, rock wool, and potting soil. The middle one on rock wool is the one that we'll use to illustrate the components of the water budget today. These plants are on load cells so that we're able to continuously monitor the weight of each set of plants and their substrate. We also had Arroyo water content, electrical conductivity, and temperature sensors, the Terrace 12s, in these substrates. Other sensors monitored light, temperature, humidity, and wind for the calculation of E that I just described. So you'll see the load cells allowed us to directly measure irrigation amounts, transpiration rates, and the change in moisture of the substrate. Now this graph shows just a single day, day 36, during our experiment. The blue line is the weight from the load cell, and the value is shown on the left axis. The yellow line shows the 6 irrigation shots that were given for that day. Each shot, at each shot, the mass of the plants and the substrate increases. Each shot was a little over 500 milliliters. So with each shot, the weight jumps 500 grams, at least with the early ones, the ones early on in the irrigation. The lights came on at 36.3, 3/10 of a day into the day, and you can see that the weight starts to drop faster as the transpiration increases when the lights come on. There isn't a lot of stomatal control in this crop, so the main effect of changing the light is to change the radiation intercepted by the canopy. The lights went off at 36.8 or 8/10 end of the day, and the slope decreased then. Now, if we take the slope of the mass versus time line, we can compute a transpiration rate. This graph shows the same data as the last one, but I've added now the water content data measured with the Arroyo Terrace 12 sensor, and that's the orange line, and you read that on the right axis. Note that the changes in water content are very similar to the changes in weight. That shouldn't be surprising, but it should give us confidence in the Terrace 12 for managing irrigation. The Terrace 12 is fairly inexpensive. It's pretty easy to install and it's easy to monitor. A load cell is much more expensive. It'd be pretty difficult to use a load cell in a commercial controlled environment situation. And in addition, the Terrace 12 gives us information on the nutrients and the osmotic stress that the load cell wouldn't be able to do. Now this graph again has the weight and the water content traces, but rather than the irrigation, it shows the drainage. We installed a tipping spoon monitor on the outflow of the rock wool block to see when and how much water came out. And it's perhaps obvious if we put 500 plus milliliters of water into the substrate and its mass and water content don't increase, the water has to be going somewhere besides the substrate. Here you see that the water content continues to increase with subsequent shots till about 50%. Subsequent shots increase it a little, but most of the added water drains out. The highest water content the substrate is able to maintain is around 54%. Now in soil, we call the upper limit of plant available water field capacity. When the water content of the soil profile exceeds field capacity, the excess water mostly drains out. While there is no field involved in controlled environment crops, the idea of a field capacity still applies. When irrigation occurs at water contents below field capacity, the water is retained for plant uptake. Water applied at or near field capacity will mostly drain out. We find the field capacity the way we showed here, by adding enough water so that the water content plateaus and drainage starts. Field capacity can change by managing the substrate water, but if we do a good job of irrigating, it'll be fairly constant during the growth of the crop. So here are some of the important points to remember relative to our water balance model and the measurements that I've shown you. First, field capacity is the water content to which substrates drain after recharge with an excess of water. If you look at the orange line in the graph here, the final shot causes the water content to reach about 55%, but the substrate quickly drains to about 54%. We therefore set the field capacity in this situation to 54%. Shots given after the substrate is at field capacity are mostly lost to drainage. Shots given before drainage starts replace yesterday's transpiration. Since we know how much water is added by an irrigation, this gives us a good way to estimate the crop water use. Now here are some additional points to remember. The change in storage term in the water budget equation is directly measured by the load cell. But we could also estimate it by knowing the change in water content that the Terrace 12 tells us and the water capacity of the substrate. Now, since we know the irrigation amounts and the corresponding changes in water content, we can estimate that substrate capacity. We talked already about the slope of the load cell line being equal to the transpiration rate during times when we're not irrigating. But again, if we know the substrate capacity and we know the slope of the water content line, we can also estimate the transpiration rate from that. Well, if we know the irrigation amounts, the substrate water content, and the field capacity, we can classify shots as recharge or as drainage. By adding up the drainage shots for a day, we get the D value for the water balance equation. If we divide the daily drainage by the daily irrigation, we get what's called the leaching fraction. And you can see that equation on the top here. And if we're irrigating with nutrient solution at a fixed electrical conductivity, the leaching fraction is the main tool that we have for controlling the electrical conductivity in the root zone of the crop. Now, to simplify this idea of how we would use the electrical conductivity, we can start by assuming a steady state and no plant uptake of salts. In that case, we can also calculate a leaching fraction from the ratio of electrical conductivities that I've shown in that top equation. In the example here then, the nutrient solution is at 3 decisiemens per meter, and if 50% of the irrigation is drainage, then the drainage water would be at 6 decisiemens per meter. Now, of course, there is uptake of nutrients, hopefully a lot of it, but this gives a feeling for the amount of drainage that would be required to bring down the root zone EC, electrical conductivity. Now with that, let's summarize the things that we've gone over today. We introduced the idea of a water budget, the inputs and losses from the soil plant system and how they have to sum to zero. This is a simple but powerful idea. We then went through term by term to quantify the terms in the water budget equation. We talked about how to check the quantity of irrigation amounts and how important it is to know how much water each plant is getting. We talked about determining transpiration rate from measured plant and environmental variables, about what field capacity is for horticultural substrates and how to determine it. With that background, we talked about ways of determining drainage and showed how to use that in connection with the known irrigation amount to determine leaching fraction, which we in turn use to control the substrate salt concentration in the osmotic potential. Now, again, thank you for being with us today. We hope you find this useful.
All right. Thank you, Gaylon. And we'd like to use the next 10 minutes or so, depending on how things go, to take some questions from the audience. Thank you again to everybody who's already sent in a question, and there's still plenty of time to submit your questions there in the questions pane, and we'll try to get to as many as we can before we finish today. Just as a heads up as well, if we do not get to your question, we still have them recorded, and Gaylon or somebody else from our team will be able to get back to you via email to answer your question directly. So feel free to submit any and all questions that you have. There are several questions. Yes, we will be sharing the PowerPoint. We will be sharing slides and a recording of the webinar to everybody who registered today. So no worries there. All right. Let's see here. One question, really quickly, are Arroyo and Taros 12 water content readings always expressed as volume per volume?
Yes.
Okay.
Yeah. It's a measure of volumetric water content.
Okay. All right. Let's see. If transpiration is high and the substrate water content reaches the minimum acceptable content during the day, how would you suggest restarting the irrigation cycle?
Yeah, I think you certainly can give irrigation shots anytime you need to, and I would do that to keep the substrate water content from going too low. That's one of the things that your system ought to be monitoring, and the examples that we've shown generally give the irrigation right at the start of the day, but I would try to irrigate in such a way that the water content didn't drop below about 30 or 35%, so that the substrate keeps doing its job properly.
All right. What adjustments need to be done if other substrates are used, for example, cocoa or other mixtures of substrates?
I think all of the things that we've talked about here apply equally well for any horticultural substrate. Typically, they have large pores, hold the water pretty weakly, and all of them are designed that way to make sure that the roots get plenty of oxygen.
Is irrigating by several shots to reach my target moisture content the optimal way to irrigate rather than giving one full shot?
It is the optimal way, and we covered this in more detail in the first lecture. You could go back and look at that a little bit, but with these coarse textured substrates, you want the water will tend to channel if you maintain them at too high a water content, and so you give small shots of water to allow the water to redistribute within the substrate between shots, and that way you get to use most of the substrate volume for the purpose that you have the substrate.
All right. This next question, I'm curious about what you said regarding intentional water stress in plants. If it's not possible to impose low soil water potentials by withholding water, you hinted at using osmolytes to lower the osmotic potential of the soil. Is this something you do in practice using certain electrolytes?
This is something that you do in practice, and we covered that in quite a bit more detail in the second lecture. But since these coarse textured materials don't allow us to apply a matrix stress for crop steering the way we might do in natural soils, we do it osmotically, and we can accomplish the same things. And in fact, that is what when people talk about crop steering, that's the meaning of that term, is to apply an intentional stress to get the crop to generatively respond.
All right. Are there any tensiometers that could be useful in substrate production to avoid plant stress?
Well, a tensiometer could be used, but because the matrix potential isn't of interest in horticultural substrates, I wouldn't use one. Water content tells you if you have a moisture release curve and a water content measurement, you know everything you need to know about the state of water in the substrate. And the thing that you need to know is the osmotic potential or the electrical conductivity, which is a separate thing, and the tensiometer can't tell you that.
Mm-hmm. Okay. If we want to reduce overall water applied per crop, what changes in monitoring or calculations are needed to account for substrate surface evaporation?
We didn't spend much time on the evaporation from the substrate surface here. The same equations apply. Need to have to know the area, the evaporative areas, and the resistances or conductances for those. But your point's well taken. If we're trying to reduce water use, then we need to quantify that evaporative area and do the things we need to do to reduce evaporation from those areas.
Okay. I think we've got time for a couple more questions here. This is about leaching fraction. Would this leaching fraction equation of irrigation EC to drainage EC apply directly to a substrate that contains and releases nutrients, or would there be more complicating factors in this case?
there are more complicating factors that the assumptions behind those calculations are steady state and no uptake of nutrients, and neither of those really applies very well in this situation that's a dynamic situation. And so the point of going through that calculation is, it's still true that the only tool that you have, if you're maintaining a constant concentration of nutrients in the irrigation water, the only tool that you have for controlling the substrate electrical conductivity is leaching. And so the point of doing the calculation is to get a feeling for what you would need to do if those assumptions applied. Now, the uptake of nutrients makes it so that you have to leach a lot less, but I think you need to understand that system, and the leaching fraction is a simplification that allows you to understand that so that you can use it to properly control the substrate electrical conductivity.
All right.
Or pore water electrical conductivity.
In the experiment you did, what was the interval between shots, and was this dependent on some climactic factor? I think this is just in general in determining that interval. What are the variables that go into that?
Yeah, we just need to wait between shots long enough so that the water can redistribute. And I think we waited about 15 minutes between shots.
Okay. Let's see. This question is saying, we know that our soil has a field capacity at negative 33 kPa. So what is the pressure point that we can take in determining field capacity of that substrate?
Yeah, that in soil we take minus 33 kilopascals typically as a kind of a rough estimate of field capacity. In these horticulture substrates, it's more like 5 kilopascals or something like that. It's an entirely different system because the outflow from the substrate is the water won't flow out of the substrate until you have a positive pressure, and so the substrate is saturated at the outflow point. And so it's an entirely different system than you have in the soil, where you have a deep soil profile with water potential gradient all the way down.
All right. And I think this is going to be our final question here. For a lot of folks, this is kind of they're new to this kind of system. So there are some concerns about how much should they worry about taking exact measurements as opposed to maybe estimating. How much will that affect their, the overall plan?
Well, that's a good question, and it's the good thing about that water balance is that that stuff still has to add up. And so let's say that you did some estimating of the E term or whichever term, you will know that the next day when you irrigate, because it'll show up as more drainage or less drainage. If you're not irrigating enough, why, you'll see that you never get back to field capacity, and that the average water content's going down. And so it's kind of self-correcting in that way, that you always will know as you go along and see the result of the decision that you made. You'll know what you need to do to adjust whatever factor you had to estimate.
Mm-hmm. All right. Thank you again, Gaylon. That's going to wrap it up for us. Thank you to everyone who submitted questions. We had a ton of questions come in, and we definitely did not get to all of them. So just wanted to let you know that, again, if we did not get to your question here during the live webinar, we do have them recorded, and we will be able to get back to you via email to answer your question directly. Please consider also answering the short survey that will appear after the webinar is finished, just to let us know what types of webinars you'd like to see in the future. And again, for more information on what you've seen today, please visit us at metergroup.com. Finally, look for the recording of today's presentation in your email, and stay tuned for future Meter webinars. Thanks again, stay safe, and have a great day.